So welcome back. I think last time we spoke I might have misspoken on one of these questions, so I'm going to go through them again. Let me set a timer for, that's good enough, okay. So, yeah. So point charge is located at some distance from point Y, so there's X and there's Y. And a charge of X experience 18 newtons towards it, so that's 18 newtons. And then just going through these questions, it says, what do you conclude about the sign of the charges? And because it's an attractive force, they must be different. We got that okay. And then what size, because if they were the same, they would be pushing away from each other, and it says that the force is attracted towards the Y. So it must be different charges. We don't know which is which, but it must be different. What is the size of the force experienced by the other object? Well, that's also going to be 18 newtons because of Newton's third law, which is, because forces come in pairs, action-reaction pairs. So that one was okay. That's going to be 18 newtons. And then what's the direction of the force on the Y point charge? Well, we just drew it in, actually, and it's going to be towards the X charge, so that one was okay. And then what can you conclude about the magnitude of the two charges? And here I just walked out and I just wondered, you can conclude nothing. I don't know if I said that, but you can conclude absolutely nothing. It's just because the forces are even does not mean to say that the charges are even. Just like, you know, when a love bug collides with your truck, the force of the love bug on the truck is the same as the force of the truck on the love bug. You can't conclude anything about the masses of the two particles by knowing that the two forces are equal and opposite. It could be anything. It could be the force of me versus the sun, or the force of me versus a butterfly. The forces of the action-reaction pair will always be the same. So I think I just can't remember. I walked out and I thought, did I say that? And then I think also there might have been something here where a point charge X is located at some distance from point charge Y, and this experiences 18 newtons. So let's just do that and do 18, and then let's do that, and then do Y. And it says, what force would charge X experience if the separation between the two charges was tripled? And so for all these, you've got to recall what the equation is, and Fe is equal to Ke big Q little q over r squared. And you can intuitively do this one. If I double my separation, then I 1/4 the force. So what force would there be? Well, if I got a new separation, unfortunately I've made this drawing, you know, and somewhere down there is the Y, is like somewhere down there. If I make this bigger, then the force would be not 18, but it would be 18 over, and what did I do to the distance? If I triple the distance, so that would be 1/9. So it would be 18 over 9, which is 2 newtons. And I think I just completely misread this question last time. I just did something completely different. Now, you can intuit that by saying it's an inverse square relationship. But the problem comes when it's too complicated to intuit. And so there's a bit of formalism comes in here. And again, we're going to have, you know, X and Y. But now we're going to mess with it. We're going to make, you know, I don't know, it says if the separation was triple, so that's going to be X, and now that's going to be way down there. That's one thing. Then it says if the charge of X was double, so let's make that bigger. And charge on Y is quadruple. So we're messing with all bits we can mess with. And what you do there is, again, you've got to know the equation, but you say the new force over the old force electrical. And we don't know the new force, we're trying to find it, but we do know the old force, so let's write it in. The old force was 18. And now we go and we say, well, this equals Ke, if you like, new. You can't really change Ke because it's a constant, but Ke new over the new big charge times the new little charge over the new separation squared divided by KE old, the old big charge, the old little charge over the old separation squared. So then the KE's can cancel. I put them down as 1 and 1. It's just habit. And then the new big charge X was doubled. So that used to be 1, and now it's 2. Clearly I could put down 1,000 and 2,000, or 27 and 54, as long as the ratio is 2 to 1. I'm okay. And then for the little charge, Y is quadrupled. So this was 1. Quadrupled means 4 times. And then the separation between the two charges is tripled. So this was 1, but we had to square it. And now the new version is 3, and we have to square it. So when I do this multi-level thing, I get 8 over 9. And it's amazing how many people will put down 8 over 9 as the answer. But in fact, we've got to go all the way back here and say, oh yeah, FE new over 18 equals 8 over 9. So FE new is equal to 8 times 18 over 9. So that's going to equal 16. 16 newtons. Yep. And just realize that, if there's an equation, I can do a ratio problem for it. I don't have to give it as just a numerical work out the answer. And in engineering, often, you double something and you have something and you triple something. You just want to get, an idea for those changes. So this is quite a decent kind of question to ask. You've got to know the equation, then you've got to have a bit of formalism. If you're not used to writing in sentences, if you just jot down the equation and somewhere else you put some numbers down, it's quite often, if you don't have this sentence, this is a sentence, or a phrase if you like, it goes something equals something equals something equals something equals something. So then if I look at that, oh yeah, there's what I want, and now that 18 is there. It's on my page, it's part of my sum. But if I just wrote down, that little bit, I'd get that bit, and then it's very tempting to say, there's my answer, So you've got to watch out for that. Okay. Cool. Well, even if we got it right last time, I think I explained it a bit clearer this time. We did the lab, and we did the lab on some fields. So we're heading there. Before we get there, let's just talk about superposition principle. If you have think of engineering and physics physics for sure tends to be made up of particles. If I have a particle and I have a whole bunch of forces on it, you might be tempted to think that this thing gets pulled in different directions, by the different forces. But it doesn't. It just knows there's a force acting on it, and it kind of balances them out and finds the net force, and the answer's just a force pointing in a direction. That's the net force. You don't stretch particles, you don't squish them. They just feel the overall effect. So if I have a whole family of forces like this, be they magnetic or be they electric or be they gravitational, it doesn't matter. I'm going to get a net effect. So how do I sum these things? And the key thing is it's not an arithmetic sum. 7 and 5 and 2 does not equal 14 unless they're all pointing in the same direction. They can cancel each other out pretty much and balance each other. So got to be careful about that. And so we have to add them up vectorially. And that's why it's a good idea to always ask yourself when a new parameter comes up, is this a vector or is this a scalar? Because how you treat it changes depending upon that. So I can do a vector diagram. We did it in Physics 1, and just to remind ourselves, these are abstractions. A force does not have a length, but we can draw it as an arrow in a vector diagram. So I have 4 forces on this caused by, well, 5 charges. There's Q1, Q2, Q3, Q4, and then there's my little charge, Q. So there's 5 charges here, 4 interactions, and we just add them up vectorially. There's this sense, I think when we first begin, there's this sense of somehow if I'm occupied interacting, say I'm holding something up here, and then somehow I have to hold something up there, and then somehow I have to balance something on there, that the more things I have to juggle with, the less focus I have on that, and so there's less interaction with that. You know, I'm somehow forgetting about that because, well, these guys are interacting and those guys are interacting and this is a mess, and it's, you know, and it's actually, it makes no difference. My interaction with Q1 is not affected by the fact I may or may not have interactions with Q2, Q3, or Q4. Doesn't matter. It stays the same. It's going to be less of the overall effect, but it's not diminished in the least bit because I have these other interactions taking place. So we just got to, in a way, it makes life very nice. We just simply say, well, okay, here's the general expression for the vector force, and let's add up however many vector forces we have. So we say the sum of all these vector forces, and the nomenclature is, we say I, where I goes from 1 to 2 to 3 to 4, to as many as you have. It's just I is an integer, it's a number. So that's how we just write it down. That's just shorthand for that. We say the net force on charge Q experiences, the net force that charge Q experiences due to a group of point charges equals the vector sum of the electrical forces caused by the individual charges. So you picture it as, you know, there's a pair there and a pair there and so on. Let me just ask you a bit of a background question here. Let's clean this up a bit. So just looking at this, what can you tell me about the sign of the charge Q1 compared with little q? They must be... What can you tell me about those 2 signs of those charges? The opposite. And what can you tell me about those 2?
Same.
They must be the same. And so on. So you just I'm just trying to encourage you to just look a little bit deeper sometimes, and, you know, sort of try and get the better. I'm really coming to the conclusion. It's not the math that limits people in this course for the most part. Most people can do the math. And it's not knowing the equations. It used to be when we had the equation sheets, it used to be that people who were decent students would say, I can figure it out. And they'd kind of come into the test and they'd look and they'd see a V and say, that's probably voltage because of what I'm studying at the moment. And occasionally they'd misinterpret, but, you know, they were an intelligent person with a little bit of background. And then when we got rid of the equation sheets, I found scores improved because people were going, I got to know that equation. And in writing down what V was, they would kind of say, oh, that's velocity, or that's voltage or something. But I think the problem is that now people sometimes will make a mistake over what the letter stands for, and sometimes they will make a mistake over the interpretation in terms of their visualization. So the more I can encourage you to actually do focus on visualization, you will just be better. However good an engineer you're going to be, you will be better if you visualize better. It's not a zero-sum gain. You're not going to be worse at other things because you visualize more. You will be better. You don't, you know, when you do your math, you're improving your math, but the payback is little because you're quite good at math already, you know. But for most people, it's the visualization that they're really just beginning in. So whatever time you can steal to do visualization will make you significantly stronger as an engineer. So I'd encourage you to do that. And speaking of visualization, here's some diagram, and this is a classic. I don't particularly like, for myself, I don't particularly like these problems. I think they're a bit, first time you see them, they seem really hard, and once you've seen them, it's like, you know. 4 equal positive charges lay at the points indicated. So these are 4 positive charges. There's 3 interactions when you think about it. Well, there's more. There's an interaction there, an interaction there, an interaction there, an interaction there, an interaction there. But there's 4 positive charges. The magnitude of the force experienced by charge X, so we're looking at charge X, caused by charge Y, so we're looking at these 2 guys here, is 3 newtons. They're all positive, so I know that basically that is 3 newtons. That just told me that. Then it says, what is the magnitude and direction of the force experienced by charge Z? So the first thing you've got to recognize is that all this stuff about charge X was giving me a scale. The question is not about charge X. That was an example, if you like. The question is about charge Z. So I look at charge Z and I say, well, there's 3 forces, there's 3 charges interacting with Z, and they're all positive, so I'm going to get a force here. I'm going to get a force there. I'm going to get a force here. This force is caused by X. This force down here is caused by W. This force up here is caused by Y. They're all going to be repulsive forces because they're all positive charges. And then I look at my diagram a bit further and I see, well, all of these are the same distance. And they're the same distance that this was down here. So if that was 3 newtons, then this is 3 newtons, this is 3 newtons, and this is 3 newtons. It says, what is the magnitude and direction of the force experienced by Z? So now I'm going into component land, and what I've got to recognize is I have, well, let's have a look. Divide this guy up into 2 components. Divide that guy up into 2 components. And that guy there is its own component. It's got no vertical component. So, let's just, doesn't take a second. This down here. So let's look at our angles. If it's a equilateral triangle, is that an equilateral triangle or an isosceles? What do you think? Equilateral. So, what's the angle between what's the size of the angles? They're all the same. 60, yeah. So a little bit of geometry. So if that's 60, that's 30. If that's 30, that's 60. If that's 60 down there. If that's 60, that's 60. So it goes, oh yeah, 60, 30, 60, 30. Did I do that right? Yeah, I did. I nearly walked off a cliff. And if that's 60 around here, then if that's 60 there, then that's 60 down here. Good, okay, good. I can look here and I can say this would be 3 sine 60. Hopefully you're kind of comfortable with that. I've got one, I want the other, and I'm using the complement of the angle between. I'm not using the 30, I'm using the 60. So it's a sine of the 60. That's 3 sine 30. 3 cosine 30. It's the same as 3 cosine 30. It's the same numerical value if I'd chosen to use this 30-degree angle instead. And down here, this is 3 sine 60 newtons. And then this guy here would be 3 cosine 60 newtons. And down there, this would be 3 cosine 60 newtons. Sum of the forces vertically equals 0 because that's plus 3 sine 60 and that's minus 3 sine 60, yeah? Might as well do it as a step. Plus 3 sine 60 added to minus 3 sine 60, which equals 0. That's where that comes from. Sum of the forces horizontally is equal to 3 cosine 60 plus 3, because that's still there, plus 3 cosine 60. So that here is equal to, what is that? 6 newtons, I think. 3 cosine 60. 1.5, 1.5, and 3 makes 6. So what I can look at this now is I know that it is 6 newtons and its direction, well, looking at my diagram, to the right. And can you see how the first time you see that, you kind of scratch your head because there's an awful lot of implied information that's not directly given. But once you've seen one, it's kind of like, you know, you kind of, it's like a joke, you know the joke, you know. It's kind of like, all right, I get what's going on. Okay. But we can, we vectorially add vectors. That's the way it is. We vectorially add vectors. In the lab, we started introducing this idea about electric field. And the idea basically is we have so many possibilities for charges that life can get really complicated. So the idea is maybe we could do a series of contours which would like help us with this. Oops, we've got to go in a circle. I messed up on that, but you get the idea, yeah? And then I can just talk about the altitude at that point is like talking about the potential at that point. So you don't need to know where the mountains are, you just need that bit of the map. And so and I used to work for an electron microscope company, and what they do is they use little wire filaments, or they used to use, they're probably all gone by now, but they used to use little wire filaments to boil off electrons, and then they'd use electrostatic lenses to make those electrons go into a nice sharp point. And that's what they used to image, you know. And so they used to have a little thing that looked like that. There's the filament, and it's giving off electrons in all directions. And to make the electrons go back into a nice sharp point, they used a little, it looked like a thimble with a hole in it. So I'm doing a cross section. And the idea is that inside that thimble, you get, basically the electrons are forced into a crossover. They want to go off in all directions, but they get forced into a crossover. And then that little spot there is the size of your beam, which is smaller than the size of the bit of the filament that's been heated up. So it's a way of focusing in. And the way they do these is they'd actually do calculations, but they'd actually plot out a whole series like we did in lab. They'd basically do a shape, and then they'd do the calculations, but basically they'd plot a whole bunch of equipotential lines. They do a whole bunch of equipotential lines, and then they do the field lines, which is what the electrons, well, the field lines are what the protons want to follow. Electrons just go the other way. And they plot them out. It was because they had quite subtle changes to the shape of this inside of the thimble would make a better beam or a worse beam. So this is the idea of being able to get, if you like, a contour map of electric fields is really valuable. And so we use it a lot. But it is an abstract concept. You can think of it in terms of numerically, it is the force that a charge would feel per coulomb of that charge. So if it's a 5 Newton per coulomb field, if you put 1 coulomb there, it would feel 5 newtons. If you put 5 coulombs there, it would feel 25. If you put 10 coulombs there, it would feel 50. You know, it is that. But it's still there even if you put no coulombs there. The field is still there. So it's not just a numerical value. It's an abstraction. And sometimes we think of it as the numerical value, and sometimes we think of it as the abstraction. So it's really quite a subtle thing. So the more we play with it, the better. So the electric field can be considered as an aura, and that's, in inverted commas, meaning, don't quote this in your PhD thesis, as an aura that surrounds a charge and is a storehouse of energy. The electric field strength E at a point in space is numerically equal to the electric force that would be experienced by a unit positive charge at that space, because you're dividing by 1. So if it was a 5 Newton per Coulomb field, and I put a 1 Coulomb charge there, it would feel, 5 Newtons. But if I put a 3 Coulomb field there, it would feel 15 Newtons. Again, the ratio is still 5 to 1. And the trick is, even if I put no field there, no charge there, I've still got the field. So we can say, well, here's our parent big Q, and here's our little q. This is a test charge that I'm just putting in there. And what we get is, your force will be that, and your test charge is that. So your electric field is equal to the force vector divided by the amount of charge. That should be a Q0, really. Amount of charge you put in there. You put Q0 amount of charge there, divide that force by that charge. Okay. The electric field strength can have units of newtons per coulomb. Clearly, newtons per coulomb falls out. What's not so obvious is volts per meter. I can justify that by saying if a volt is energy per coulomb, so it's joules per coulomb, and I divide that by meters, and a joule, of course, is a force times a distance, so it's going to be a Newton meter per coulomb per meter. So that goes to newtons per coulomb. So I can justify that. If it walks like a duck, it talks like a duck, it quacks like a duck, it's a duck. So these guys are equal to each other. If I'm in SI units, numerically a field in newtons per coulomb equals the numerical value of that same field in volts per meter. So it's a nice bridge sometimes. If you think about our diagram with newtons here and newtons per coulomb here and joules here and volts there, it's a nice kind of bridge, isn't it? Taking you across that little square diagram. So it's a useful thing to keep in mind. So what we say is that the electric field strength E can have units of newtons per coulomb and volts per meter, and or volts per meter. These have the same dimensions. And then by substitution and expansion, we can see that the separation between the mother charge and the point of interest affects the electric field in an inverse square law. So if F is equal to KE big Q little q over r squared, and my field is equal to the force I get divided by the charge that's feeling that force, and my electric field is equal to KEQ over r squared. But that field is there whether or not that charge is, the little charge is there or not. You don't need, the electric field is about the space surrounding the mother charge. It's not about the little charge. The little charge may feel it. It's like, I hate to tell you this, but when you're not there, the mountains still are, you know? You don't make the mountains are there, and you feel the effect of them, you know? Gravitationally, you know, the earth pulls you. The earth's still there whether you're there or not. Now, yeah, you also pull the earth. So this little test charge, if the test charge is there, is creating an electric field. And that's affecting the mother charge. But we just, you know, we don't mix those together. Big charge, field with big charge, put the little charge on it if you want to. Little charge little electric field. Put the big charge there if you want to. Or have the big charge with no little charge. You still got an electric field. Have the little charge with no big charge. You still got a different electric field. So there's a lot going on here, and it's kind of like sometimes you think about it in just numerical terms, and sometimes you're visualizing things and sketching things. And the better you can do those things and just get comfortable with it. It's not the math. This is sums. It's not the math. It's what the symbols really stand for that count. So let's imagine we have a large point charge and a little point charge. A large point charge Q establishes an electric field. So we say the force of A on B, well, I didn't mark my A on B, is equal to KE, oh man, big charge, little charge, over R squared. And the situation gives that. Applying E that means defined as. Three little lines means defined as. It's not just equal to. We defined it as being equal to. As that, and so we end up with that. So that just explained what we did on that previous page. What is the magnitude of the electric field at a point 3 meters from a 6 Coulomb positive? 6 positive. I'm here 3 meters away. Want the magnitude. Magnitude of the electric field. Let's have a look. Q is equal to plus 6 coulombs. R is equal to 3 meters. Let's have a look. I want my electric field. E is equal to I don't know. There's two ways you can do this. You can turn around and say, well, Fe is equal to KE Q over R squared, and then say E is equal to Fe over little q. So E is equal to KEQ over R squared. You can know that one well and know that definition and derive that one. Or with practice, if you do the homework, it's not that much. You get to till you know that equation. So I say E is equal to KEQ over R squared. So E is equal to 9 times 10 to the 9 times Q, and Q was plus 6 over R squared, and the R squared is going to be 3 squared, which equals 6 times 10 to the 9, and its units are going to be newtons per coulomb. Now, before we move on, there is nothing at that point. There's nothing there. And that's the one disadvantage of this is if you're thinking about it as Fe and then you say, well, I've got to divide by Q. What's the Q? You divided whatever Q you needed to cause the Fe. So I think that's where a little bit of the issue can come from. So in a way of explaining it, it also sometimes, if you're not careful, obscures it a little bit. If I was to double my separation, can you tell me what the electric field would be if I was twice as far away? If it was here? Twice as far? Can you do it? Look at your expression. Ask yourself, how does R go with the thing? Is it an inverse relationship, an inverse square relationship, inverse cube relationship? It's an inverse square relationship, so it's going to be not half of my answer, but 1/4 of my answer. So 1.5 times 10 to the 9 newtons per coulomb. Yeah? If I tripled it, it would be 6 over 9 times 10 to the 9. If I 4 timed it, it would be 6 over 16 times 10 to the 9. Does the direction matter? Absolutely not. In my mind's eye, I have, volcano. It's a pity we don't live in Arizona. That's right, just look out the window and you see it every day. It's like that. The actual direction, are you there? Are you around here? Who cares? You just... So, supposing we have more than one of these things. Is it a vector? Electric field is a vector. It's got a magnitude and a direction. So we need to just add them vectorially. Superposition principle. Again, I'm not, So this says 3 equal positive charges lay. Now there's only 3 charges, because we don't need the 4th charge, because this is our point of interest. Indicate a diagram. So the electric field. So here's an issue. Okay. The electric field at any point 2 meters away from any individual charge is 6 newtons per coulomb. So this is my point of interest. Only consider x. Should my arrow go towards x or away from x? Only considering x and z. Forget w and y. Only considering those two. Which way will my arrow point? I'm going to point away. And what's the justification for that? Why do you know it's away from x? Because x is positive. Think of positive charges as being mountains, and the electric field is the effect on a boulder. Boulders roll down mountains, so you're going to roll away from the volcano. So it's going to be downhill. It really helps. When we get to voltage, we're doing that same visualization. So that, and then this guy, well, it's going to be away from there, and this guy is going to be away from there. And I know that this is 6 newtons per coulomb, and I know that's 6 newtons per coulomb. I know that that's 6 newtons per coulomb. And I change colour pen so I can show my... Oh man, change colour pens, find your fingers. Let's have a look, purple. So I change coloured pens so I can say, oh, look at that, there's one vector, and oh, look at that, there's another vector component, and oh, look at that, there's one vector component, and oh, look at that, there's the other vector component, and I know that this here is going to be 6 times the sine of 60, and I know this is going to be 6 times the sine of 60, and I know this is going to be 6 cosine 60, and I know this is going to be 6 cosine 60, and I know that this is 6. So the sum of the electric fields vertically equals 0 newtons per coulomb. The sum of the electric fields horizontally is equal to 6 cosine 60 plus 6 plus 6 cosine 60. So that equals 12 newtons per coulomb to the right. The same problem, isn't it? The thing is, so it's just getting you to practice a bit of components, And it is true. You've got a diagram and you've got to interpret it. From that respect, it is true, yeah. What's attracted to what?
If the force was not repulsing but attracting.
What force?
Well, I guess the electric field.
See, good point there. There is no force on point Z because there's no charge on point Z. It's a complete abstraction. And so can you see, what you're doing is exactly, you're not the only person, in fact, we all start like that. It's like we introduced the field through the force. So now we're talking about the field, and even though we don't put a charge there, we can still go, well, there must be a force there. But there's no force there because there's no charge. If I had put a charge there, the force would depend upon what sign of charge I put there. And if I put a positive charge there, it would be a repulsive force. if I'd chosen to put a negative charge there, it would have been attractive.
Professor?
Yeah.
Just clarifying for myself, so Z is just an arbitrary point in space,
Z is a point in space. There's nothing there.
so for the sake of the problem, we ascribed it a positive charge.
No, I didn't. I've not mentioned charge at all. I've only talked in terms of field. So let's just review that a little bit. Yes, we started off with charges, two charges, and we got forces. And then we said, let's invent this thing called electric field. And to get the size of it, we said, well, it's the force that this guy would feel if it had a charge of 1. So that gives us a scale for the electric field. But the electric field is like not to do with this force. It's like, 900-foot contour line is there whether you're there or not. It's about the mountain. So the electric field is about those three charges, not about the space. And that just is something where it comes in, unless you're really focused on it, I think most students will trip over that for a long time.
Oh, wait, so we're creating a scalar.
It's an abstraction.
An abstract
It's
unit for scaling, so that we understand essentially the altitude. If you
It's a
will.
vector. It is a vector, but it's a if you like, it's telling you the size of an effect.
Right.
So just watch out for that. Yeah.
So if you put a charge of 1 coulomb in Z.
Yeah.
I'm sorry, 6 columns,
6 coulombs.
6 coulombs.
Okay.
Then you get a positive, you get a 12 Newton force positive.
I get 72 newtons because it's 12.
Okay.
What that tells me is it's 12 newtons per coulomb, and you're putting 6 there.
And what if it was negative?
It would be if you put a positive charge there, it will be 72 newtons to the right. And if you put a negative charge there, it'll be 72 newtons to the left.
So it'd be negative 72 newtons.
I'd sooner you didn't say that because I don't know what negative means in this case. And that's why I'm saying it's a vector, so that's why in my answers I have to the right or, potentially to the left.
Okay.
If you define to the right positive and to the left negative, then that would work, but we're not necessarily going to have that. So again, another wrinkle. Now are we talking about scale of the magnitude of it, or are we talking about the vector of it? Right. And let's make it more interesting. So, okay, I have a cloud of charge, not just 3 charges. Let's have 1,000,000 charges. So finely divided, it's a cloud of charge. And I want to know the electric field caused by all those charges on this one little point in space. So here's my cloud of charge in blue, and here's my point in space. There's no charge at that point in space. It's just like, take the entire Appalachian Range, and I want to know the rolling effect on a boulder that's in Atlanta. It's like, okay. So I've got to take all of it into account. So each little bit has its effects. Not sure that's a good example, but anyway. We divide the continuous charge distribution into small elements, delta Q, little bit of charge. The electric field due to one of the charge elements at point P is given by. So here we imagine having a little cube with this charge, so small that the front is near the back and the left is near the right and the top is near the bottom. Doesn't matter. So I say, well, it's going to be KE, my little bit of charge. This is now the mother charge. This guy here is now the mother charge. Not this guy down here, there's no charge down here, and not the whole thing. This is my mother charge for this little bit of the problem. So it's KE delta Q over the separation between that little bit of charge there and that, so that's R squared. And then there's a vector effect, so I've got to put down my unit vector. My unit vector just says, oh yeah, by the way, it's in that direction. So it's in that direction. So the total electric field, we'll just do this a whole bunch of times, so it's the sum of this each time you do it. You just get a computer and add it up and you can do it. And in reality, if you have something like that, you're going to iterate it. You're going to basically define 1,000,000 points, and you're going to pick a point in space, and you're going to go that effect and 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 that effect. And you can do it 1,000,000 times until you get your answer. And then you're going to move to another point. You're going to do the same thing again. Another point, and do the same thing again. That's iterative effects. That's what computers are great for. And, you know, there was a time when you'd wait a week for that answer, and now you can kind of get it a lot faster. And it's got a value. I think they're sometimes called ab initio. That iterative methods can be really good. There are some pitfalls, but they are tremendously, when used well, they're tremendously good. Unfortunately, or fortunately, when you go to the more physicsy world, well, in many cases there are symmetries. So you don't need to do this. If the cloud's got a nice shape that you can live with, why bother doing this iterative technique? Just use math. And so in the limit, we would go from this iterative method of summing to actually doing some kind of integration. Yeah? And there's so just before we go on, so there is a bit of it's not a dilemma particularly, but there is a bit of an issue, and that is, so my background is I'm a physicist, and I did applied physics as an undergraduate degree, and then I did semiconductor science material science as my PhD, and came to the States and worked in engineering departments. Material science and engineering is one, both NC State and also at UF. And so I hung around a lot more with engineers. And I think I may have told you in Physics 1 that at first I was not impressed by what I saw in the engineering department, because it seemed like it was craft. They did pottery and they did, you know, casting little decals and stuff like that. It's like, oh my word, what's going on? And then I found out that actually, no, whereas I knew there's a solid, they actually know there's different types of solid and different properties and all that. I remember there was a course called Material Selection, and I thought it was, well, you get a catalogue and you look it up, you know. But material selection is actually, you know, what type of metals are there and what are the different physical properties and how do we characterize them and all that. And it's really valuable, you know. It's how you make machines work. It's materials that make machines really good. Use the wrong material and you can really, really hamper yourself. So the person who became one of my mentors was a boss I had there who was basically an engineer, but had spent time. He clearly spent time in physics departments, and he knew what was what. And we're talking one day, and he was saying, "Yeah, I think the problem because it was just, you know, computers were coming in. I mean, I'm that old. The computers were coming in, and as they came in, all these techniques became, you know, really much more accessible. And so we were talking about the value of using computer iterations to actually solve a problem, or going to first principles and using symmetries to solve it. And he basically said that, in his opinion, that the physicists tend to hold on to calculus a bit too long, and they don't iterate when they could do, and so they tend to look at simplistic systems. But on another hand, he was worried that engineers would become computer jockeys all the time and would do a computer program when they could actually just do some integration. So he said, I don't think either one uses the other one enough, and you've got to be good at both, you know. So your calculus classes are not wasted, but if you're not done them already, you'll be doing some computer classes which will make you much more powerful in the real world, and just embrace them both. It's a shame not to be able to do something because you don't have your computer with you, when you can do it in the back of an envelope and vice versa. There's a classic joke. I'm going to stop this. So here we are. Consider a rod. Let's get to a pen, and let's go back one. So consider a rod with a uniform charge totaling 9 coulombs. The rod lays on the x-axis. It extends from +3 to +7. Big Q is 9 coulombs. I used calculus to show that the electric field at point P, which is located at +1, is that. And this is kind of what the question will say. I'll only have you in a straight line. I'll only have you in line with the rod. I might put you to the right of it. I might put you to the left of it, you know. The idea is this. First thing you do is you say, well, I know that my electric field is equal to the integral of Ke dq over r squared. Let's remember that. Let's go back and just double check on that. Ke dq over r squared on the bottom. That little q became a dq, didn't it? So Ke dq over r squared. And sometimes that causes people issues because I don't know how you were introduced to it, but I was like introduced to it as like the dx was almost like just a squiggly line and a dx at the other end, and they're both just like magical little symbols. But for us, that dq is a little bit of charge. It means something. The squiggly line is still a magical symbol as far as I'm concerned. But that dq is like, it's a physical thing. And where is it on my diagram? Where is that dq on my diagram? That dq is there. It's that little bit of charge. And, okay. I have no idea how to integrate that. I have no idea. How do you integrate Ke over r squared with respect to dq? It's like, how do I integrate bananas with respect to machine guns? It's like, I got to convert. How many bananas make a machine? I've got to do that conversion. So what I do is, again, I look here for the physicsy bit. I'm going to call this little width here dr. Now, the physics explanation is that my little bit of charge, which I want to get rid of, is equal to my little bit of length multiplied by, I'm going to say, little charge is equal to little slice or width times linear charge density. So that's where that comes from. So I'm saying, well, my little bit of charge is equal to my little bit of width times my linear charge density. Well, that's my total charge over my total length. Oh, let's put those two in. My total length is there. That's the physicsy bit. So, let's take that and substitute that here. So E is equal to the integral of Ke over r squared dr q over L. I just substituted for that dq that. Let's rearrange a little bit. Ke is a constant, so bring it outside. Q's a constant, bring that outside. L's a constant, bring that outside. The integral of 1 over r squared dr. So this equals Ke q over L, the integral of r to the minus 2 dr, which equals Ke q over L. And let's have a look. That goes to, what, raise the power by 1 and put it in the denominator. So that would be, let's have a look, minus 1 over r. Am I right on that? Goes to -1, put it in the denominator, yeah? Am I right? You happy with that? R to the -2 goes to R to the -1, -1 over -1, yeah? So it goes -1 over R, yeah? So, oh, I need some numbers. So E is equal to, and we're going to say KE, Q over L, that would be 9 over, what is my L? What is the value of L? Is it 3? Is it 7? What is the value for my L? What is it?
4.
Yeah, it's 4, isn't it? It's 7 minus 3. Let's put that down so we remember it. 7 minus 3. And then let's have a look. -1 over, and what is, oh, I'm sorry, no. Duh. I'm sorry. Going back here, I missed a step. I need to have my limits. What is the longest, biggest value of R? First of all, where is R on my diagram? Where does R start and where does R end? For this particular example, where does R start and where does R end?
3 and 7.
Any other bids? That's the separation, isn't it? That's where it comes from in our original equation. Yeah, R was the separation. Yeah. So what am I separating? What am I distinguishing between? What am I measuring between on my diagram?
From P to the,
From P to wherever my little shady thing is. Yeah. What's the longest that R value can be? Goes from 1 to 7, so that's 6. And what's the shortest that R value can be? Move that over and over and over. What's the shortest that R value can be? From 1 to 1 to 3. So that's 2. So imagine just sliding this thing over here. That's the one extreme. Slide the thing here, that's the other extreme. Ask yourself what the value of R is. So, then we come along here. I made a mess of this. Let's get a thing and just clean this up just briefly. I've still got time, I think. Here it is. Let's go here. Pen. So that's going to be -1 over 6 -1 over 2. So this is going to be 9 over 4. That's going to be -1 over 6 -3 over 6. E is going to be 9 over 4. Should be KE up there. 9 over 4. -1 minus 3 is -1 plus 3, which is plus 2 over 6 KE. So that's going to be 18 over 24 KE, which equals 3 over 4, which equals 0.75 KE newtons per coulomb.